All right, so we have more solving equations. So this week we're starting out in chapter 7. There's a link to the textbook here. I usually pop it out into a window. And we're using identities, and we're just going to keep adding some more. So today is a review of solving equations plus a few new kinds of equations we haven't really seen before. And then we're going to just start adding on these important formulas for trigonometry, the addition and subtraction identities, double angle identities, and then we'll do more modeling, which we've already done some of, but we're going to do a few more complicated problems there. Important things here, again, the unit circle is going to pop up often in terms of analyzing our different solutions. So just to review, suppose we had, let's say, the sine of theta is equal to -1/2, and we want to find 4 solutions. I recognize -1/2 as a special value from my special angles. So when I think about applying the inverse trig function here, theta equals the arcsine of -1/2, or we could call it the sine inverse of -1/2, pops into my head an angle related to the square root of 6. Sorry, pi over 6, not the square root of 6. So thinking about the unit circle, on the unit circle, the sine is a y value. So we're thinking about, all right, where is y equal to -1/2? And that would either be at this point here, which is the one the arcsine knows about. And good morning, Emily. But we also have this other point over here where y is -1/2, and then there's a couple of ways we can get to that angle. So let's use a different color here. There's my radius. So I could make a positive angle to get there. So that would be one way to do it. But I could also come around and point that out with a negative angle. So reminder, this right here would be -pi/6. Choose red for that version. That's the one the arcsine knows about. And the other solution related to the sine is always going to be pi minus what the arcsine thinks. So let's think about that for a minute. Pi minus the arcsine for the other one. Oops. Let's use blue for that one. So the arcsine believes the angle to go with the ratio of -1/2 is -pi/6. So that gives us pi minus -pi/6, which is pi plus pi/6. And pi/6 could be viewed as 6pi/6. So then another solution here should be 7pi/6. And that's going to be this positive version of the angle to get to that other point here. And think about that. We take pi gets us to here, and then we move that reference angle pi/6 further. That gives me the pi plus pi/6, or 7pi/6 here. We could have found that angle a different way. We could have gone around -pi and then added pi/6. So another solution here, let's maybe use green for that one. By just looking at the symmetry of the circle, if I sweep around -pi, right, so I come around clockwise, but then I back off, I go positive pi/6, that should get me to that same point. So that would be -5pi/6 should be another one. I could get to this angle here by going around 2pi to get back to it in either direction. So I have so far 1, 2, 3 different solutions. So I could do 2pi plus my first solution. That would be what? 12 pi over 6 minus pi over 6. So 11 pi over 6 would be another one. And so bottom line is, once I have the first two solutions, I can keep making new ones over and over again. So in general, for this one, I have the arc sine version. Let's call that theta 1. And that's negative pi over 6. And then theta 2, that's due to the symmetry of the circle, the pi minus what the arc sine said. So that one is 7 pi over 6. And any other solution is a version of this one or that one. So in general, I can add 2 pi to this over and over and over. Same thing here, 2 pi. And k is just any integer. So k could be 0. In that case, I get like negative pi over 6 or 7 pi over 6, but k could be 1, like I added 1 pi over 2 here. K could be 2, I could add 2 pi over 2's, and so on. But I could also go the other way. I could go around clockwise, negative 1, negative 2. And so this formula, these two formulas right here are going to give me all possible solutions. Let's look at a graph and double check that. Desmos does a good job when the special angles are involved. So I'm going to call it f of x equals, we just started off with the sine of x. And I want to know when that's equal to negative 1/2. So I also have to graph y equals negative 1/2. So we found our arc sine solutions. So the first one we got here was the negative pi over 6. And then we used the symmetry of the circle to get this one over here, the 7 pi over 6. So those are the first two related to the arc sine and the symmetry of a circle. Now consider the 7 pi over 6 one. That happens on the downhill part of the wave. So every solution that's on the downhill part is going to be related to the 7 pi over 6. So this one over here would be 7 pi over 6 minus 2 pi. This one over here would be 7 pi over 6 minus 2 pi times 2. And then over here on the edge, that would be 7 pi over 6 plus the period of 2 pi. And then this one happens on the uphill part of the curve. And so every other solution related to the uphill part is going to be related to negative pi over 6. So the next uphill one here, so that's pi over 2 later. There's one right off my screen. That would be another, sorry, not pi over 2, 2 pi later. And then uphill, this one right here would be my negative pi over 6 minus 2 pi to get to there. And then if we looked out this way, the next one would be here. That would be minus 2 periods. So from here we go minus 2 pi minus another 2 pi. So there's all my possible solutions based on the first two. So in this chapter, we're just going to look at some more complicated equations and see what we can do to solve them. All right, so let's consider something like twice the sine squared of theta plus the sine of theta is equal to 0. So now we have multiple trig functions and one of them is squared. So that kind of poses a difficulty. It turns out though, we know how to solve equations like this if we just think for a second about equations we've seen in the past that look like this. All right, so these are very similar. Here I'm just saying, well, let's, instead of the sine of theta, let's just call it x. So if I had to solve 2x squared plus x equals 0, well, I would factor this or use the quadratic formula. I'm going to factor it. So I can factor an x out. That's going to leave 2x plus 1 here equals 0. And then we have what's called the zero product rule, which says you have product equal to 0. You can break it down into each factor is equal to 0. So one solution would be x equals 0. Other solution would be 2x plus 1 equals 0. Subtract 1, divide by 2. X equals negative 1/2. I can apply the same idea to this up there. All I did here was say, let's replace the sine with x. So this equation up here is going to also break down to the sine of theta equals 0, just like the x equals 0, or sine of theta equals -1/2. And then I can finish it up. I can say, okay, well, what values of theta give me 0? What values of theta give me -1/2, right? We already did that one right there. But let's just look at that one more time without the x's. If I start with something like twice sine squared of theta plus sine of theta equals 0, I can realize I can factor this right here with the sine. I can pull out a sine of theta, and that's going to leave behind twice the sine of theta plus 1. So just like I factored before, this time I'm factoring a sine instead of an x. Zero product rule applies, so I can break this into two different problems on that multiplication. One problem would be the sine of theta equals 0. And the other one would be twice sine of theta plus 1 equals 0. And we solve stuff like this in the last chapter. We subtract our 1, divide by 2, we get sine of theta equals -1/2. Now, unlike the problem with the x's, we were done here, but we have one more step here. We got to apply the arc sine to get theta, because theta is what we're solving for. So here, I want to know when the sine is equal to 0. So remember, think about the unit circle. We should know this one. Sine is a y value. For what angles is y 0? Well, that would be here, theta equals 0, or here, theta equals pi. And then multiples of, if we then add or subtract the period to that right there, we can generate more. But I got two solutions, two basic solutions there. This one we solved earlier. We discovered that theta was either equal to -pi/6 or theta was equal to 7pi/6 from our previous example. So I have 4 different basic solutions to those. And if I want more, I just start using the period of the sine to get more. So if we need more solutions, then what we're going to do is add multiples of the period to any of those. And the basic solutions come from thinking about the unit circle. One of them of each of those is going to come from the arc sine. So for example, this one right here is what the arc sine would tell us if we plugged it into the calculator. And this one right here is what the arc sine would tell us. We plug it into the calculator. And the other two solutions here came from symmetry of a circle. What other point is related to sine y equals that number? What other point on the unit circle is related to our sine as a y value on the unit circle?